Hello students, welcome to EPG Pathshala. I am Gaurav Gupta from Sharda University. Today we are going to talk on module Inventory Models, Quantity Discounts under paper Operations Management. This chapter would help students to understand application of quantity discount model of inventory management. Second, assumptions of quantity discount model. Third, calculation of optimum batch size and minimum total inventory cost. Introduction. A fruit vendor sells a particular fruit at rupees 50 per kg. Thus 2 kg of fruit is sold at rupees 100. But at the end of the day, the vendor, due to perishable nature of product and intention to clear the stock, is willing to sell 2 kilograms of same fruit for rupees 80. If a customer is interested in buying more than 2 kgs, vendor is willing to reduce price further. The question for customer is how much he or she should buy and at what cost. Being more would might result in fall in total cost, but it also increases holding and maintenance cost of larger bulk of products. These similar questions of how much and at what cost have been answered in other inventory models. But in those cases, a particular size of quantity was ordered at constant price. There was no fluctuation in prices of product with change in size of order. But in practical situations, especially in case of perishable products or products which are produced and sold in high quantities, discounts are offered by the manufacturer depending on size of order. In these cases, a special inventory model called as quantity discount is applied to answer the questions of ordering optimum quantity at lowest cost.
Quantity discount model. Quantity discount model examines the effect of price incentives given in case of larger quantities of products ordered. Thus, in such model, only those problems are discussed where price fluctuation with regard to size of order. Larger the size of order, more would be the discount offered. Larger size orders would help in reducing ordering cost as frequency of orders would be less but increases holding cost as larger number of units would be stocked. The model tries to provide a quantitative solution to balance the trade-off between holding and ordering cost. Following illustration would help in understanding the working of model. For example, a supplier is selling first Q equal to 1000 units at a price of rupees 10 per unit and then offers three discount plans which are discount 1 Q equal to 0 to 1000 units rupees 10, discount 2 Q equal to 1000 to 2000 rupees 9.50, discount 3 Q more than 2000, discount rupees 9. As it can be seen from above data that price of product is not fixed and with varying quantity of product order price keeps changing. With change in price of product, total cost get affected. The total cost curve for three different discount levels have been shown in figure.
Total cost curve for three different discount levels. The figure explains following points. First, 1000 units are being offered at rupees 10 per unit and yields first U-shaped total cost curve indicated by total cost curve for discount 1. The total cost curve drops down with increase in quantity and reduction in price per unit as shown by first price breakpoint at 1000 units. The cost U-shaped curve for this situation is shown by total cost curve for discount 2. Lastly, at second price breakpoint occurring at 2000, total cost curve falls further as indicated by total cost curve for discount 3. The result is a total cost curve with steps at the price break.
Issues in estimating best lot size. The figure also illustrates EOQ level indicating estimation of optimum batch size at minimum possible cost. The EOQ shown in figure do not necessarily produce the best of lot size for two reasons. 1. EOQ is not feasible. The estimated lot size at particular price point which would result in minimum costs might not correspond with quantity offered by the supplier. For instance, point A in the figure indicates that by buying at price of rupees 9.50 per unit, number of units to be ordered per batch would be less than 1000. But this quantity at rupees 9.50 is not feasible for the supplier. So order size has to be increased from A to minimum 1000 units to avail discounts. Total cost is not feasible. Suppose estimated batch size calculated at particular price point is feasible for supplier. For instance, EOQ comes out to be at 1750 units at rupees 9.50, which is feasible as it falls in the range offered by the supplier. But its total cost is higher than the price breakpoint, for instance 2000 units. Then even in the case of EOQ being feasible, batch size with lowest total cost would be ordered.
Procedure used to find the best lot size. Step 1. Calculate the EOQ for each price level until a feasible EOQ is found. In the above example, calculate EOQ for rupees 10, rupees 9.50 and rupees 9. If the calculated EOQ falls in the range of units offered by supplier, then the EOQ is feasible. As discussed, EOQ of 1750 units at price level of rupees 9.50 was feasible, implying batch size of 1750 unit lies in the range corresponding to its price. Step 2. Calculate total cost for each price break quantity If the calculated EOQ is feasible for first discount level, then total cost should be calculated for the quantity and for larger price break quantity at each lower price level. If calculated EOQ is feasible for second discount level, then total cost should be calculated for that quantity level and higher break quantity. The quantity given lower total cost would be considered as optimum batch size. Derivation of quantity discount model. In quantity discount model, items price is not fixed as assumed in EOQ derivation. Larger the batch size, higher would be the discount offered. Thus, total cost is a direct function of price per unit of the product. In the model, total cost is combination of three costs, namely holding cost, ordering cost and production cost.
Holding cost. Between time period of start and end of cycle, time period T on an average at any particular unit, Q divided by 2 units are being held up in inventory. If to hold 1 unit holding cost is H, then annual holding cost equal to average inventory level into holding cost per unit equal to Q upon 2 into H. The holding cost in the model is specifically in terms of percentage. As costlier the item, more would be its holding cost. Ordering cost. Suppose annual demand of an item is 1000 units and manager orders 100 units per order. Thus, she has to place an order 10 times. Thus, D divided by Q represent number of orders. If S is setup or ordering cost per order, then annual ordering cost equal to number of orders per year into ordering or setup cost per order equal to D upon Q into S. Product cost. If P is the cost of 1 unit of product and D is the annual demand, that is total number of units ordered per year, then total product cost would be PD. Thus, total cost equal to annual holding cost plus annual ordering cost plus product cost. That is TC equal to Q upon 2 into H plus D upon Q into S plus PD, where Q is lot size, H holding cost of 1 unit, D annual demand, S ordering or setup cost, P price per unit. To find minimum possible cost, the above equation is differentiated with respect to Q and simple minima calculus is applied to find out batch size Q, which would be Q equal to root of 2ds upon H. This formula of Q would provide manager the most optimum batch size that should be ordered with minimum total annual cost. Practical examples. Example 1. A supplier has introduced quantity discounts to encourage larger order quantities of an item. The price schedule is order quantity 0 to 299, price per unit is Rs 60. Order quantity 300 to 499, price per unit 58.80. Order quantity 500 or more, price per unit 57.
the supplier estimates that its annual demand for the item is 936 units. Its ordering cost is rupees 45 per order and its annual holding cost is 25% of the item's unit price. What quantity of the item should the company order to minimize total cost? Solution: find the first feasible EOQ starting with lowest price level. EOQ 57 equal to 2ds upon H equal to 2 into 936 into 45 divided by 0.25 into 57 and its root equal to 77 units. A 77 unit order actually cost 60 per unit instead of 57 per unit used in EOQ calculation. So, this EOQ is not feasible now. EOQ 58.80 equal to 2ds upon H, its root, equal to 2 into 936 into 45 divided by 0.25 into 5 8.80 and its root equal to 76 units. This quantity also is infeasible because a 76 unit order actually cost 60 per unit, so try the higher price level. EOQ 60 equal to 2ds upon H and its root equal to 2 into 936 into 45 divided by 0.25 into 60 and its root equal to 75 units. This quantity is feasible because it lies in the range corresponding to its price P equal to 60. Step 2. The feasible EOQ of 75 does not correspond to the lowest price level, hence we must compare its total cost with the price break quantities 300 and 500 units at the lower price levels 58.80 and 57. Total cost equal to Q upon 2 into H plus D upon Q into S plus PD. Total cost equal to 75 upon 2 into 0.25 into 60 plus 936 upon 75 into 45 plus 60 into 936 equal to rupees 57284. Total cost 300 equal to 300 upon 2 into 0.25 into 58.80 plus 936 upon 300 into 45 plus 58.80 into 936 equal to rupees 57382. Total cost 500 equal to 500 upon 2 into 0.25 into 57 plus 936 upon 500 into 45 plus 57 into 936 equal to 56,999. The best purchase quantity is 500 units, which qualifies for the deepest discount. Following table indicates the discount offered by the supplier for various quantity. Suppose data and cost analysis shows an annual holding cost of 20%, an ordering cost of 49 per order and an annual demand of 5000 units. But order quantity should be selected. Discount Q equal to 0 to 999 units rupees 5. Discount 2 Q equal to 1000 to 2499. Discount rupees 4.85. Discount 3 Q equal to more than 2500. Discount 4.75. Solution. Step 1. For each discount category,
compute batch size, that is Q, using EOQ formula associated with quantity discount model. EOQ at P equal to 5.00 equal to 2 ds upon H and its root equal to 2 into 5000 into 49 divided by 0.20 into 5 and its root equal to 700 units. The quantity is feasible because it lies in the range corresponding to its price P equal to 5. EOQ at P equal to 4.85 equal to 2 ds upon H and its root equal to 2 into 5000 into 49 upon 0.20 into 4.85 its root equal to 711 units. At 711 unit, order actually cost 5 per unit instead of 4.85 per unit using in the EOQ calculation, so its EOQ is not feasible. EOQ at P equal to 4.75 equal to 2 ds upon H its root equal to 2 into 5000 into 49 divided by 0.20 into 4.75 its root equal to 728 units. A 728 unit order actually cost 5 per unit instead of 4.75 per unit used in EOQ calculation, so this EOQ is not feasible. Step 2. Calculation of total cost. As discussed, total cost would be calculated for the feasible quantity, that is, where the discount offered is viable, and also for the quantity break points. In this example, Q equal to 700 units is feasible and Q equal to 1000 and Q equal to 2500 units are the break points. So by using total cost equal to Q upon 2 into H plus D upon Q into S plus PD, total cost TC at Q equal to 700 and P equal to 5 equal to 700 upon 2 into 0.20 into 5 plus 5000 upon 700 into 49 plus 5 into 5000 equal to 350 plus 350 plus 25,000 equal to 25,700. Total cost at Q equal to 1000 and P equal to 4.85 equal to 1000 upon 2 into 0.20 into 4.85 plus 5000 upon 1000 into 49 plus 4.85 into 5000 equal to 485 plus 245 plus 24,250 equal to rupees 24,980. Total cost at Q equal to 2500 and P equal to 4.75 equal to 2500 upon 2 into 0.20 into 4.75 plus 5000 upon 2500 into 49 plus 4.75 into 5000 equal to 1188 plus 98 plus 23,750 equal to rupees 25,036. Thus, it can be seen from calculations that at Q equal to 1000 units and each unit being sold at discount price of 4.85 total cost in minimum, a batch size of 2500 units does offer maximum discount, but larger batch size results in maximum holding cost, thereby making it second best solution. The example illustrates following two very interesting characteristics of quantity discount model. The feasible batch size does not necessarily result in most optimum total cost. With increase in batch size, holding cost keeps increasing and ordering cost keep decreasing. A case on
quantity discount model of EOQ. In this chapter, we shall analyze a company's inventory control problem and apply our proposed method in solving our problem. The aim is to determine the maximum discount price that should be taken and the quantity that should be ordered giving the quantity discount. The general practice is that most establishments do not analyze the quantity discount that companies offered them with their carrying cost. They either go for it or reject it by the discretion of people or departments in charge. These are basically inefficient as carrying cost may be high or low. Economic order quantity EOQ is a pure economic model in the classical inventory control theory. The model is designed to find the order quantity so as to minimize the total average cost of replenishment under deterministic demand and some simplifying assumptions. The study focuses on inventory management when the unit purchasing cost decreases with the order quantity Q. The main objective of the study is to model economic order quantity with quantity discount to achieve optimum level of inventory. The model was analyzed against the current practices of an organization ordering policies to find out whether it is appropriate to go for quantity discount when offered. The management of the organization wants to determine if it should take advantage of the discount or order basic EOQ order size offered to them by their suppliers.
Suppliers of non-security examination materials occasionally give discounts to the organization in the line with its organization policy in order to reduce a large stock of its material, which may increase its holding cost. In 2012, it offered a quantity discount pricing schedule as shown in table below. Quantity 1 to 49, price 1400. Quantity 50 to 89, price 1100. Quantity 90 to 349, price is 900. 350 and above, price 890. The annual carrying cost for the organization for such material is 190, the ordering cost is 2500, and annual demand for a particular model is estimated to be 200 units. The management want to determine if it should take advantage of this discount or order the basic EOQ order size. We first determine the optimal order size and total cost with the basic EOQ model. S is equal to 2500, H equal to 190 per material, D equal to 200 materials per year, where S is equal to the ordering cost, H is equal to carrying cost, D equal to annual demand, P equal to price. Q equal to optimal quantity. Q equal to 2 ds upon H and its root 2 into 25,000 into 200 upon 190 its root equal to 72.5 material. Although we will use QOPT equal to 72.5 in the subsequent computation, realistically the order size would be 73 materials. This order size is eligible for the first discount of rupees 1100, therefore this price is used to compute total cost. Total cost equal to Q upon 2 into H plus D upon Q into S plus PD equal to rupees 233784. Since there is a discount for a larger order size than 50 units, the total cost of must be compared with total cost with an order size of 90 and a discount price of 900. Total cost equal to rupees 194,105. Since there is a discount for a larger order size than 90 units, this total cost of must be compared with total cost with an order size of 350 and discounted price of 890. Total cost equal to 212,678.57.
So students, let us now summarize what we have learnt in this module. Quantity discount model is the appropriate model of finding optimum batch size, which would result in least possible total cost when supplier offers differentiating price. With increase in batch size, supplier might offer a batch size at discounted price. In such cases, manufacturer might be lured to buy larger batch size. But this also results in higher holding cost and lower ordering cost. Thus, it becomes necessary to resolve such a dilemma quantitatively by using quantity discount model. Before deriving for the most optimum batch size, the chapter has also discussed two issues that should be understood in the model. Firstly, the calculated EOQ might not be feasible as though it results in lowest cost but might not correspond with the discount offered by the supplier. Secondly, total cost calculated at EOQ might not be the lowest total cost. These issues were resolved quantitatively by discussing derivation of the model and illustrated through some practical examples. Thank you.